Magicians fool us with sleight of hand and optical illusions, and we love it. We allow them to trick us, to make us believe falsehoods. They pique our curiosity and entice us to try to unravel their deceptions. That's the way it is in the world of magic. But when it comes to science, whether physical science or social science, we don't want to be tricked. We want to know the truth.
Collectively, as scientists, we have the goal of uncovering a lot of truths about the world and the way people function in the world. A lot of this information has practical implications, has profound effects on the way people live their lives, the way people handle medical conditions, the way they learn to navigate situations that might come up for them. We have a responsibility to make sure that we disseminate our findings as cleanly, clearly, and accurately as possible, but it's also the case that there are some limitations.
When researchers reach conclusions about the phenomenon that they're interested in studying, they disseminate these findings to the scientific community and also to applied communities, whether it be in medicine, psychology, or some other applied field. Sometimes these results accurately reflect reality, and that's when the ideals of science have been met. When a particular set of results gives you good, accurate information about what's really happening in the everyday world. Other times, however, results don't accurately reflect what's really truly happening in the outside world. Usually this happens because there were one or more aspects of the design of the study that cause reality to be obscured. It's important to remember that results can be misleading no matter how careful the researchers have been.
How results can be misleading. Problems in experimental methodology. Even carefully designed studies can yield misleading results. Let's examine elements of research design that will strengthen the accuracy of your own research and help you watch for possible pitfalls when reading published research findings. Specifically, we will talk about issues in selecting participants and assigning them to experimental conditions, as well as the importance of replication of results. Within our discussion of participants, we will explore the characteristics of a sample, including strategies for selecting participants, the difference between population and sample, and why it is necessary to narrow the number of participants in the study. We will discuss random selection in its three forms: simple random sampling, stratified random sampling, and proportional sampling. Next, we'll look at how our samples could turn out not to represent the population we think we're studying, and could thereby produce misleading results. In the second part of this DVD, we will examine how the way we assign participants to experimental conditions could cause us to reach misleading conclusions. We will examine the risks involved when participants select their own conditions, paying close attention to individual differences variables and exploring ways to minimize this risk, such as random assignment to condition. We will also talk about factors that vary along with the manipulation that may really be responsible for the results we attribute to our experimental conditions. Fortunately, we can minimize the effects of such factors by measuring the factors and by employing the yoked design. Finally, we'll see how replication of studies helps make sure that our results are not misleading. Understanding these risks and strategies improves our ability to reach meaningful conclusions and empowers us to read other researchers' reports more critically. Characteristics of a sample. Selecting participants. A population consists of every individual human being, plant, animal, or natural phenomenon that is part of your specific area of interest. In social science, it is the group of people you're trying to learn about, the complete group of participants who can be studied. It includes everyone of interest, so the group is very, very large.
If you're interested in the ability of infants to recognize their caregivers' voices, then your population is all infants everywhere. If you're interested in the ability of blind infants to recognize the touch of a caregiver, then your population is all blind infants everywhere.
The ideal approach to answering a question would be to test every single individual in the population of interest. However, that would require an unrealistic amount of funding and manpower. Instead, we run our studies on a sample and then generalize those results to our population.
A sample is a subset or a portion of the greater population in which you're interested. You choose your sample in a way that it allows you to generalize to the greater population of interest.
For example, in a presidential election, it would be ideal if you could poll every single voter and ask them how they plan to vote in the upcoming election. Of course, this approach would likely give you a very accurate answer as to how people would vote, but you might imagine it would be incredibly expensive and time-consuming. Instead, you want to select a sample from the population of registered voters in order to make a prediction about who might win the election.
We choose the sample with the purpose of generalizing to the whole population. However, the sample may not fully represent the population we intend to study, which could bring about misleading conclusions.
If your population of interest is all blind infants everywhere, you might sample from a pediatric ophthalmology clinic in the area where you live. The crucial issue here is that your sample might not actually be representative of the entire population of interest. Maybe this ophthalmology clinic serves only wealthy patients, and you can't necessarily generalize the experiences of the blind infants in wealthy families to all blind infants everywhere.
Characteristics of a sample. Random selection. The primary way to ensure that the results of our sample generalize to our population of interest is to employ a technique called random selection. Random selection is a method of selecting participants that ensures that every member of the population of interest has an equal chance of being part of the study. Researchers usually use one of three types of random selection: simple random sampling, stratified random sampling, and proportional sampling.
In simple random sampling, every single person in the population of interest has an equal likelihood of being contacted to participate in your study, and this is without any exceptions. There are a couple of different ways of contacting participants so that everybody has an equal chance of ending up in your study. The first way is to use a random number generator, which you can find online, in order to generate random telephone numbers, which you'll then call in order to invite people to participate in the study. The second way is to use a lottery system in which you have all possible phone numbers, and each phone number has an equal likelihood of being selected.
In stratified random sampling, we randomly select participants from sub-samples of the population. So for example, if we want to measure all registered voters on their voting behavior in an upcoming election, it makes sense that we want to make sure to sample equal numbers of Democrats and Republicans. So if our total sample size is 20,000, we want to make sure we sample 10,000 Democrats and 10,000 Republicans.
As with all other aspects of research design, a researcher must share the results of the study along with the caveat that the sample was drawn using stratified random sampling.
In proportional sampling, we randomly select from the population, making sure to select individuals based on their representation within that population.
In our voting example, we probably would want to select a sample of voters that includes proportional representation of various sectors, selecting randomly within those subpopulations. For example, if we know that 50% of registered voters are Caucasian, 20% are African American, 20% are Hispanic, and 10% are Asian, we would want to make sure that, likewise, 50% of participants in the study are Caucasian, 20% are African American, 20% are Hispanic, and 10% are Asian. How results can be misleading. Non-representative samples.
It's very important to remember that the results that you find are specific to your sample, and they're only true for the general population to the degree to which you have a truly random sample that is representative of the greater population. It's actually very difficult to truly get a random sample for a couple of reasons. It's difficult to get a truly random sample because most researchers are studying individuals who live in the same city as the researcher.
If you're interested in the attitudes of nurses toward older patients, you might select a sample of nurses who are at the local hospital where you are. It would be very impractical and quite rare for a researcher to travel around the entire country. What that means is there might be something different about the nurses at your local hospital that isn't also true for nurses everywhere. Even if you were able to sample from all hospitals across the United States and measure nurses in all of these different settings, it's highly unlikely that you would also sample nurses at hospitals in other countries around the world. And there might be things that are very different about nurses in the United States compared to nurses in other parts of the world.
As cultures differ around the globe, the attitudes of local nurses likely will reflect the attitudes of the general population when it comes to how they regard elderly members of society, for example.
Another reason it can be difficult to get a truly random sample is that most researchers don't actually have an exhaustive list of all the individuals in the population of interest. For example, if you're interested in studying the development of infants, you might have a list of all infants born at a local hospital or a list of all infants born in your state within the past year, but you're not likely to have lists of all infants born in the entire United States in the past year.
Even with an exhaustive list of the entire population of interest, it may not be possible to reach everyone.
Some people don't have telephones, and there might be something very different about people who don't have telephones compared to people who do. If you're only able to reach the people who do have telephones, then you don't know anything about the characteristics of that other set of people who don't have phones.
Going back to the voting example, it could be that individuals living in poor, rural areas are more likely to vote for a particular candidate and would in fact turn out by the thousands on election day. But many of them may not have telephones. If our sampling method has not enabled this segment of the population to be represented sufficiently, we could have misleading projections.
Even among the people who do have phones, it isn't always possible to reach those individuals. They might be working at times of day that make it difficult for them to answer a phone. There might be something different about people who are available to take a call in the middle of the day compared to people who aren't. So for example, stay-at-home parents might be available to take a call in the middle of the day, but there might be something different about them compared to people who aren't stay-at-home parents.
In addition, there is almost certainly something different about people who agree to participate in a study relative to people who don't. It could be that by nature they are more likely to make time to help a researcher. They could need the money that is offered as compensation for participating. Or they may have a special interest in psychology or other social sciences. These qualities may affect our results, even if at first they don't seem relevant to our topic of study. Assigning participants to experimental conditions. One of the most important elements of a study is the assignment of participants to the experimental conditions. Let's look at an example of ways participants can be assigned to experimental conditions, some problems that can arise, and strategies to make the results as accurate as possible.
Let's say that I'm interested in weight loss among obese patients. And I'm interested in two approaches to weight loss. The first approach is an exercise program where I have people engage in cardiovascular exercise, calisthenics, weightlifting, etc. And in the second approach, I'm interested in diet with lots of fruit and vegetables, low carbohydrates, etc. Ultimately, my research question is which works better for weight loss among obese individuals? Is it the exercise program or is it the diet program? Now, the easiest approach to studying this would be to select participants from weight loss programs around the country that specialize either in an exercise intervention or in a diet-based intervention.
By tracking patients' weight loss from pre-program to post-program, we could observe a correlation between the degree of weight loss and each of the program types. The problem is that rather than being randomly assigned to experimental groups, participants are choosing their own conditions. This self-selection can bring about misleading conclusions.
If I find that the patients in the exercise program ended up losing more weight than the patients in the diet-based program, then this result could be due to one of two things. The first possible reason is that, in fact, exercise is a better intervention than diet. And that would answer my ultimate research question, and that would be wonderful. However, there's another potential reason why I may have found this difference, and that reason has to do with something called individual differences.
Individual differences. Individual differences, personality traits such as motivation and self-discipline, or physiological traits such as metabolic rate or percentage of body fat, are variations that occur naturally across individuals in a population. When they come into play in a research study, it may be these additional variables, rather than the intervention or the experimental manipulation itself, that are partially or entirely responsible for the differences in results across experimental groups.
It could be that people who choose to sign up for an exercise program have higher levels of motivation. So when we find differences between the exercise program and the diet-based program, it could be that it's simply the exercise program that is superior, or it could be something having to do with motivation.
Random assignment to condition. Assigning participants to condition randomly helps minimize the effects of individual differences variables on our results. When participants are part of an experimental study, they may be assigned to a control group or to one or more experimental groups. As researchers, in order to make sure that we are not biasing the results by choosing which participants should undergo each condition, we employ techniques to achieve random assignment to condition.
A hallmark, or perhaps the hallmark, of experimental research design is something called random assignment. If you don't have random assignment to different conditions, then you don't have an experiment.
There are many ways to achieve random assignment. From the tried and true act of flipping a coin, which yields each participant a 50-50 chance of participating in either of two groups, to more technologically advanced methods, such as an online random number generator, which would assign conditions to participants. No matter which method we choose, we must be sure to be true to our assignments. Even if a patient comes in and says he or she loves to exercise or confesses to binge eating after exercising, we must still assign that patient randomly, whether that means the exercise program or the diet-based program. Making even one exception would undermine the validity of our study.
By randomly assigning your participants either to the exercise-based program or the diet program, you increase the likelihood that individual differences, all individual differences, be it motivation, self-discipline, or any other factors that may impact weight loss, are equally distributed across those two conditions of your experiment.
Now the average value of each individual differences variable will likely be the same across experimental conditions, so we can be more confident about our results and better able to draw conclusions about the impact of the intentional manipulation.
Random assignment makes it more likely that individual differences variables will be equally distributed across your conditions. But it doesn't necessarily guarantee that those important variables will be equally distributed. Even if we do what we're supposed to do, which is randomly assign participants to the different conditions of our study, we might still end up with unequal levels of those very important variables across the conditions of the study.
Any individual differences variable that is unequal across conditions could be responsible for observed differences between groups at the post-test.
The best way to minimize the risk of those individual differences variables is to actually go ahead and measure them. Now, in order to do this, obviously, you have to know a lot about the phenomenon that you're studying. So if I am interested in studying weight loss, obviously I'm going to have to know a lot about the physiology of weight loss, the psychology of weight loss, important variables related to exercise or diet, I'm going to have to be very familiar with all of the variables within those variables that may be unequally distributed across my groups, and I'm going to want to measure them in my participants to make sure that my groups are equal on those variables.
Ideally, we would measure each one of these variables and then, using statistics, test whether they are equal across the 2 or more experimental groups. For example, if there are unequal levels of metabolic rate across the groups to begin with, then that could be the cause of differences across the 2 groups. A good consumer of research recognizes that these alternative explanations dilute the power of a study's conclusions.
There is a second possible approach. If you suspect that there is an individual differences variable that could impact your results, you can impose certain restrictions on random assignment.
In our weight loss example, we could control for an individual differences variable such as motivation by finding a way to measure each participant's level of motivation at the outset and make sure that there is an equal number of high motivation participants and of low motivation participants in each group. We would randomly assign the individuals to groups with the caveat that for every high motivation participant in a given program, we would force assign a low motivation person to that program.
There is a potentially serious problem in that there's no way to control for absolutely every individual differences variable that could have an effect on the results.
Even if we were the world's leading authorities on weight loss, there are sure to be some individual differences variables that we don't know could impact weight loss. For example, let's imagine that marital status impacts the efficacy of weight loss programs. If we didn't know this, then it would never occur to us to make sure that we had the same number of single, married, divorced, and widowed participants in each of the groups. If exercise appeared to have better weight loss results than diet, but it happened that there was a higher percentage of married participants in that group, we wouldn't know that marital status, rather than the program itself, could be responsible for those results. As researchers, we could publish our conclusions without being aware of that individual differences factor, and we would be misleading anyone who read our study. Factors that vary along with manipulation.
There's also the problem of other factors that might vary along with our manipulation. Although we expect and hope that our manipulation causes changes in the variable of interest, it's also true that sometimes the manipulation can also cause changes in a different variable. It wasn't the manipulation itself that caused the change or the difference between the groups. It was some other factor that varied along with the manipulation.
A factor that varies along with the manipulation changes along with the variable of interest and may be responsible for the observed results. For example, if participants in the exercise program lose more weight than those in the diet program, we're likely to conclude that the exercise itself is the causal agent or ingredient, but there could be another variable that is involved. It might be that very high levels of exercise lead to increases in metabolic rate, and that it's the higher metabolic rate, however it might be achieved, that is causing the superior weight loss.
This is a real problem for drawing cause and effect conclusions. In this case, the truth behind the phenomenon would not have been uncovered, and so the ultimate goal of science has not been met.
Minimizing the problem. There are 2 ways to limit the risk of misleading results due to factors that vary along with the manipulation: measuring the factors and controlling for the factors through the yoked design.
Researchers can choose to measure the factors that they think might vary along with the manipulation and then test to see whether those factors were equal or unequal across the groups.
If we, as researchers, are concerned that as the experiment progresses, participants in the diet-based program will become more depressed than participants in the exercise program, we can measure levels of depression each week and test for whether the 2 groups score differently. The problem here is that if there are differences between the 2 groups, then we'll know that there may be an alternative explanation for our results, but there's nothing we can do about it. The strength of our conclusions is irrevocably weakened. A better option in this situation is to control for potential factors that vary along with the manipulation.
Yoke designs are a very creative way of experimentally controlling for certain factors that might impact your results if they differ across two conditions. Let's say, for argument's sake, that vitamin D impacts weight loss. And again, we have the participants who will be engaging in an exercise program and the participants in a diet-based program. Now, of course, if we have participants in the exercise program outside for, say, 3 hours per day exercising, they're going to be receiving much more vitamin D than the participants who have not been asked to exercise outside. And it's these varying levels of vitamin D that might impact their weight loss. What we can do with a yoke design is to actually force a situation in which we pair participants in the exercise program and the diet program. So let's say that participant 1, who's been randomly assigned to the exercise program, spends 3.5 hours a day outside exercising. What we would do is we would have the yoked participant in the diet-based program engage in their calorie-restricted diet, but actually just spend 3.5 hours per day outside, not exercising, but simply getting sun exposure in order to control for that amount of vitamin D. If the second participant in the exercise program arrives and that person is spending 2 hours per day outside, then we would have their counterpart in the diet-based program also spend 2 hours per day outside, not exercising, but simply in order to control for the amount of vitamin D that that person is getting. So at the end of the experiment, say that we've gone through 60 pairs of participants with whom we've done all of this, at the end of the experiment, what we can be sure of is that it was not sun exposure and vitamin D that caused differences between our two conditions. It was actually, hopefully, the intended manipulation.
Of course, some factors are easy to yoke, while others are impossible. For example, it would be very difficult and highly unethical to make a participant in one group depressed in order to balance the depression in his or her counterpart in the other group. There also is always a risk that there is some factor of which we are unaware that varied along with our manipulation, and therefore we failed to yoke participants in a manner that could be crucial to producing accurate results.
There's always the problem of extraneous variables. No matter how well designed a study, no matter how meticulous a researcher, no matter how careful the investigators are to control for all variables that might actually account for their results, it's always possible to miss an extra variable or variables that might in fact account for the results. The scariest thing is that we often don't even know that we're making erroneous conclusions because the third variables, those extraneous variables, often aren't even known.
The importance of replication of results.
When we replicate our experiments, we increase our confidence in our results. Individual differences variables are unlikely to be the culprit multiple times in the same way. So if we repeat the experiment with different samples, with different populations, in different settings, and we still see a similar pattern of results, we increase our confidence that the manipulation actually is causing the outcome.
As a consumer of research, if you find studies that reach the same conclusion using slightly different procedures or conducted by different researchers around the country, then clearly your level of confidence in that particular finding is going to increase.
A general rule is that you should take results with a grain of salt unless they've been replicated.
Conclusion. Non-representative samples, individual differences variables, extraneous variables, and factors that vary along with the manipulation are among the problems that can lead us to reach inaccurate conclusions. While it's impossible to make our studies 100% foolproof, researchers can minimize risks by judiciously employing strategies such as random selection, stratified random sampling, proportional sampling, random assignment, yoked design, and replicating our experiments with different samples and populations. As scientists, we cannot rely on trickery to make people believe us. We sincerely aim to learn about the truths of the world around us, to make our research as accurate as possible, and to share our findings with the world of learners and researchers.